Okay, the paper I'm presenting is Measuring and Modeling Anisotropic Reflection by Ward in collaboration with Lawrence Berkeley Laboratory. Okay, so what does this paper do? It presents a new device for measuring the BRDF. It measures the BRDF of various anisotropic materials. It proposes a model for fitting that data to. It then fits that data to that model. And finally, it presents a method of rendering based on that model. So it presents a full pipeline going from physical material to rendering that material. Now, the paper first starts with the talk of empirical and theoretical models and how one of the failures of theoretical models at the time is that it wasn't easy to go from data to rendering. And this paper wanted to change that. It talks a little bit about what the BRDF is, but we don't need that. Then it talks about the standard way of measuring the BRDF of a material, which is with the GAN-IO reflectometer. And because BRDF is a four-dimensional function, that means that the light and the measurement device have to rotate along two angles to get all of the information that you need. And the problem with this is that it's very expensive. You can see that an isotropic measurement would have cost a few $100s, while an anisotropic measurement would have cost a few $1,000s. And the reason there's such a huge discrepancy there is because an anisotropic measurement requires all 4 degrees of freedom, while an isotropic measurement only requires the angles from the normal to the devices. Okay, so the idea that LBL had was that you could play with optics to capture all of the measurement for a single light angle at once. And the way they do this is best shown in this figure. So there's the light source here, and that's projecting onto the sample, which is right here. And then the sample will reflect these rays in a bunch of different directions onto this hemisphere. This hemisphere is a mirror, and that means it'll reflect the rays very predictably, and you can do some geometry to determine the angle that the ray has when it hits this measurement device. And the measurement device has a lens which captures data from the entire hemisphere and projects it onto an image. You can then do a whole bunch of geometry to calculate where each pixel of the image came from. They talk about some of the limitations that this device has. It isn't great at measuring grazing angles. And this is because the materials and the geometry need to be pretty precise to capture those correctly. It also isn't great at surfaces that are very mirror-like. The reason that it isn't great at this is because the light source they used causes the light to like spread out before it even reaches the surface. Traditionally, this is avoided with use of a laser. Now that you have the BRDF data, you need to fit it to a model. So the solution that Ward came to was a modified version of an existing solution. So the existing solution, which was for the isotropic case, was just a Gaussian model, while the idea is that if you take that Gaussian and you stretch it along one axis more than you stretch along the other axis, that is, you make it elliptical, this will be enough to model the anisotropicness of the material. And they run it through an approximation, and you can see the results of this here. So, so what are these figures? As you go from one figure to the right, you're increasing the incident theta by 30. And the incident theta is the angle from the light to the normal. And as you go from one figure on the top to the figure on the bottom, you are rotating the incident light around the normal by 90 degrees. Why 90 degrees? Because that is the amount it takes for the angles to be linearly independent. The x-axis of these graphs is the theta of the viewer, which is the angle from the normal to the viewer. The triangles are the measured data points, while the dashed line is the fitted model. The model is fitted according to a least square error fit, and as you can see, the fitted model does actually fit pretty well, although the data is pretty noisy. Okay, now that we have the model, we need to render it. So the rendering is what they call a hybrid approach, and it's a blend between a deterministic and a stochastic approach. The deterministic one is what we're used to. So the best way I can explain the difference between these is with this image. So the left image is the deterministic approach. The middle image is the stochastic approach. The right image is a blending of the two together. The deterministic approach gives a very smooth look, especially for the specular highlight, but most of the image is pretty plain. While with the stochastic approach, seems to be a lot more like variation, and the specular highlight is like very bumpy. And when you combine the two together into a blended result, you get the advantages of the not very plain looking most of the ball. We get the specular highlight that's very smooth. And the noise actually acts as like a tail for the highlight. Right, the chair on the far left is an actual photograph. The chair in the middle is rendering with a deterministic isotropic Gaussian model. The chair on the right is rendering with the anisotropic hybrid approach proposed in this paper. And you can see it looks much closer to the photograph than the isotropic approach. And here is a complete scene. Finally, a couple tables are presented which describe how a few materials that they sampled have been fitted to their model. So you could then take these values and render them accordingly.